Okay, so happy Thursday. We'll take a look at section 12 today. We finished up 11 pretty quickly last on Tuesday, so that went well. And then I don't know for sure that we'll get all of section 12 covered during class today. Seems very possible, seems likely, but it's a little bit longer than section 11 was, so maybe not done as early. Anyway, so we'll take a look at this section. Let's see. So section 12 is triangles in neutral geometry. And when we talk about neutral geometry, what we're referring to here is just Euclidean, which will, that's where we're working right now. We'll take a look at how things change a little bit later. But start off with the definition. What is a triangle? Well, a triangle is defined by any three non-collinear points. The triangle, defined by the points A, B, and C, is simply the line segments A, B, unioned all together. So A, B, B, C, and A, B, C, C, A. There we go. So the union of all the line segments. And it's just a collection of, take your 3 points, and from them create 3 lines, and the 3 lines create the triangle. Nothing surprising. So congruence of triangles. 2 triangles, A, B, C, and D, E, F, are congruent, denoted using our usual notation for congruence, if and only if. Now, what follows might change depending on what definition you're looking at exactly, but we're going to use the most thorough description right now, and we'll say that they're congruent if and only if all of the angles and all of these sides are congruent. So notation is important here, so we want to be able to say that angle A, B, C is congruent to, actually we can write this a little bit easier because we're just looking at the 3 points. We can say angle A is congruent to angle B, angle B is congruent to angle E, need angle there, angle E. And then angle C is congruent to angle F. So that takes care of the angle congruencies. And then we want to state that the sides are congruent, which amounts to the side lengths being the same. So AB is equal to DE, and BC is equal to EF. And CA is equal to FD. Okay, so that gives us our congruence of 2 triangles. It is important that we pay careful attention to the notation in the order. So when we say angle ABC, or sorry, triangle ABC is congruent to triangle DEF, we are specifically saying that the angle at the first point is congruent to the angle at the first point. So specifically, angle A is congruent to angle D. If we had said triangle FED, we would be saying angle A is congruent to angle F, angle B is congruent to angle E, and angle C is congruent to angle D. So we do want to be careful about that, not just give arbitrary orderings of the name. So be careful about that. All right. So Pasch's theorem simply states that if we have a line that intersects ABC, triangle ABC, at some point such that that point is on the line from A to B, then we must have that line L intersects AC or BC, right? If it passes through one side of the triangle, it's going to come out the other side. So it's either got to come out here or it's got to come out there. So L intersects AC or BC. Okay, cool. So a prose proof. So this proof doesn't have, it's not a two-column proof, it's a prose proof. So we're just going through and discussing how, what happens in the proof. So the first thing is we're going to be using this diagram or this image to help us. So look at this when we're thinking of that, that's absolutely fine. But what we want to do is we're going to provide a proof by contradiction. And to do this proof by contradiction, we're going to assume that it doesn't intersect either one of the sides. So if it doesn't intersect BC and it doesn't intersect AC, then we would actually have that, right? If it doesn't intersect BC, then the line, right, ignore that crossing, but then we would have that B and C are on the same side of the line L. Similarly, since it doesn't cross BC, then we would have that line AC is on the same side of L, but we have that same side is actually transitive. So we can say if B is on the same side as C and C is on the same side as A, then we have that A and B are on the same side of L, which is clearly a contradiction because P, the line L passes through P, which is between A and B. Okay? So that's what's going on in our proof. So we'll write that up. So since we have that P is between A and B, we can say that A and B are on different sides of L. All right, so we've specifically said that they're on different sides with a clear reason. So suppose, right, we suppose for a contradiction, suppose that L does not intersect the line AC or BC. Okay, so since we have that, then A and C are on the same side of L. Again, A and C are on the same side of L because the line that connects them does not cross L. Okay, so we know that they're on the same side. So A and C are on the same side of L. And B and C are on the same side of L. Again, because the line connecting B and C does not cross L, because L doesn't cross BC. Excellent. Hence, right, we use this transitive idea. If A and C are on the same side and B and C are on the same side, then A and B are on the same side. Actually, no, there's no one in here, so I'm going to go ahead and take this off. Much better. Okay, so A and B are on the same side of L. But this is a contradiction because we said up here that A and B are on different sides. So, well, not so. I can say contradiction. I like to be excited when I say contradiction. Contradiction, right? What did we have here? Well, right? Those two things contradict each other. We don't have to clarify in a prose proof. You could if you wanted to. We can't have the A and B are on the same side and on different sides. That is the contradiction. So thus, what we supposed must not be true. It must not be true that L does not intersect one or the other, in which case it does intersect one or the other. So thus L intersects AC or BC. Okay, now really quickly, is there anything wrong with this proof? Look at the last line that I wrote, and then nod your head up and down and say, yes, Dr. Reinhardt, there's something wrong with what you did there. Now, there's nothing wrong with the sentence itself in terms of what I'm trying to say, but the problem is with how I said it, because the letters AC and the letters BC represent a distance. So let's just emphasize notation here that we need the lines above AC and BC to refer to the line segments. That's all. So nothing significant, but a detail that is important. Oh man, I feel so much better without the mask on. It's almost easier to talk. Can you understand me a little bit better too? Awesome. Doesn't make a difference? Well, that's good to know as well. Okay. All right. So anyway, yeah, keeping moving forward. Interior of a triangle. We looked last time at the interior of an angle, and we said that the interior of an angle is the intersection of everything on one side of a line and everything on the other side of the line, giving us this overlap. That was the interior of an angle. And we have to remember that for our definition of the interior of a triangle, because what we do is we recognize that a triangle is 1, 2, 3 angles, right? So we just want to say the interior of the triangle is the intersection of the interiors of those 3 angles. So it is the set, the interior of angle A intersected with the interior of angle B intersected with the interior of angle C. So that makes sense. All right, so we have the crossbar theorem. So the crossbar theorem is somewhat similar to Pasch's theorem. Pasch's theorem said that if we have a line passing through one side, it's got to come out one of the other 2 sides. Whereas in the crossbar theorem, what we're interested in is the line passing through a point instead of a side. So if we have some point P that's in the interior, and we look at the line passing through A and P, then the line has got to go out the opposite side. And that's what that theorem is going to say.
I have a question.
Give me just 1 second. This thing is kind of annoying with the volume. Try and talk again.
Testing.
No, still can't hear you. Give me 1 second. All right, now talk.
Hello, can you hear me?
Um,
Anything?
Here we go. Yeah.
Yeah. All right.
Oh yeah, great now. Great.
All right. Cool. So it's labeled as a theorem, and then it's called Pasch's axiom. Isn't there a difference between theorems and axioms?
Oh, what a fantastic question. I didn't even notice that. Let me share my screen again so we can take a look at that. Yes, so Pasch's axiom, and it's called a theorem. What I suspect is that Pasch didn't realize that what he was stating could be proven.
Oh, okay.
To state it, and so he called it an axiom. And someone else probably came along and said, well, we can actually prove that.
Right.
Making it a theorem instead of an axiom. I suspect that's what happened.
Okay.
But that is a fantastic question. I really enjoyed that. Yes, an axiom is something that we are assuming to be true, that it can't necessarily be proven.
Right. Yeah, and I mean, it makes sense that he would just kind of assume that, just kind of assume this and brush it off to the side and whatever. That's I mean, if you have the drawing there, it seems pretty assumable, but if it's proven, all the better, I guess.
Yeah, exactly. So that's fantastic. Again, very good question. Um, we'll look at a theorem. No, the next axiom that we look at actually talks about the same sort of idea of when we can make assumptions and when we can prove things. So we'll take more of a look at that. Anyway, okay, so I'm going to stop this share a second. So the issue is when I use the projector here, I plug it in and the audio then goes through the system. However, for some reason, Zoom doesn't utilize that particular speaker and I can't adjust the volume when I'm plugged into the projector. So then it just, anyway, so if you have a question, it's not a problem at all. I just gotta do that change up. All right, so let's try this again. Go back to here and get this over. Okay. So we have the crossbar theorem, which we said amounts to us taking a look at a triangle and saying that a line passing through the interior and one of the angles has to go out the other side. And that's what we want to say right at that spot. So we want to say that the line or the ray AP intersects the opposite side BC. So this is not empty. So that is AP intersects BC. So this would have been A, B, C here. Some point. All right. We're skipping the proof. I suspect if you really wanted to, it would look really similar to this proof. Yeah, okay. So side angle side postulate. So what the side angle side postulate says is that if we have two triangles where we have congruent side, congruent angle, congruent side, then the two triangles are congruent. So we only need two sides and an angle, two adjacent sides and an angle there to determine that two triangles are congruent. So it's, I think that we're familiar with this, but we don't necessarily think of it as a postulate. Usually we assume that it's an axiom. But in this case, it's actually not an axiom. Or sorry, it's not a theorem. It is actually an axiom. And so you might ask, well, is it an axiom because we don't want to prove it or because it's too hard to prove? Well, no, no on both accounts. So there's actually situations where all of the previous theorems and all of the previous axioms hold, but side angle side does not necessarily. So let me just emphasize this. I'll read that. The easiest way to show that an axiom has to be an axiom is to present a model in which all of the previous theorems are true, but the new axiom is false. So if we could use all of the previous theorems to prove this, making it a theorem, then we would not be able to create a space where all of the previous theorems and axioms are true and this one is false. Right? If we wouldn't be able to do that if it were just a theorem. So what we do is we recognize that in all of our axioms and definitions and theorems that we have so far, we do not ever specify how to measure distance. That's never been given. We've talked about it, but we've not actually specified. So we can use what's called the taxi cab metric, which amounts to, if you want to calculate the distance between 2 points, you measure how far over and how far up you have to go. So for example, the distance from 3,1 to 4,2 wouldn't be square root 2, the length of this hypotenuse. Rather, we would say the distance is we move over 1 and up 1, so the total distance is 2. It's called the taxi cab metric because if you think of city blocks, right, you can't drive through this, you have to stay on the roads, and that's how you find your distance when you're driving a cab, so, or any car. So that's why it's called the taxi cab metric. All right, so if we do that, then notice here that the distance, let's see here, let's label some points. So let's call it A, B, C, and D, E, F. Then we notice a few things. Let's notice a couple side lengths. AB, distance from B to A, I guess, doesn't really matter too much, is 2. Right? That is just the straight line distance of 2 using the taxi cab metric or our regular metric. The angle BAC is equal to 90 degrees, and the distance from A to C is equal to 2. So we have this triangle, call it BAC. That would be fine. And then here, if we look at the distance from E to F, that distance is 1, 2, because we're using the taxi cab metric. The angle from, let's see here. Yep, okay. The angle at E, right, this angle is 90 degrees, so angle FED. And the distance from E to D is over 1, down 1, so that distance is 2. So according to side angle side, if it were a theorem, these two things would be congruent. But these two triangles are not congruent, right? This one is larger than that one. Excellent. So this is why we know that it is an axiom instead of a theorem, because if we assumed all the previous theorems, we would be able to use this. Now, taking the side angle side postulate gives us that the taxi cab metric is not an appropriate metric in our space. Okay, but prior to that, there was nothing saying that we couldn't use a taxi cab metric. So it was perfectly acceptable, but this would violate the side angle side theorem. So it's not a theorem, it's an axiom. All right, so if that wasn't confusing, excellent. If it is, if there are any remaining questions about it, just let me know. But hopefully that clarifies a little bit that we have to take the side angle side postulate as a postulate. Again, postulate and axiom do essentially mean the same thing. Okay. The isosceles triangle theorem says that two sides of a triangle are congruent if and only if the angles opposite the two sides are also congruent. So notationally, let's see here. Two sides are congruent if, well, I guess that's not the one I had good notation for. Anyway, so if we have a triangle, call it A, B, C, and we say that AB is congruent to BC, then we're saying that we must also have the opposite sides. So angle C is opposite of side AB, and angle A is opposite side BC. Those two angles, A and C, must also be congruent. Okay. Sides are congruent if and only if angles are congruent. All right, so the proof of this is a two-column proof. And of course, this should be a double arrow. So to prove the forward direction, we're going to assume that two sides of the triangle are congruent. So the first thing to do is make our assumption. Let's assume that AB is congruent to, we'll call it CB. And that's simply given. All right, the next step, the angle bisector theorem tells us that there is a point somewhere in here that if we were to draw a line from B through P, that these two angles would be congruent. Right? This angle and that angle are congruent. They're equal to one another. So there exists point P, let's call it point P, such that the ray BP bisects the angle ABC. Okay. And again, that's because of the angle bisector theorem. All right. So this ray, by our previous theorem, was it the previous theorem? Yes, the crossbar theorem. By the crossbar theorem, it's got to cross through the opposite side. So it's got to cross through AC. So we'll say that ray BP intersects the line segment AC at some point, we'll call it D. And this is by the crossbar theorem. So we said that that was some point D. That's what we said there. There are 7 steps to this proof. There's just an unfortunately small amount of room here. All right, so step 4 is, let's label some angles here a second. We mentioned already that this angle and this one, angle 1 and angle 2, are congruent because it was the angle bisector theorem that gave us the line or the ray BP. So we have that angle 1 is congruent to angle 2, and this is simply the definition of a bisector. All right, so we have so far that this side is congruent to this side. We were able to get that these two angles are congruent. And then the next thing we need is we're going to say that these, right, or the line segment from B to D is congruent to itself. So BD is congruent to BD. Now, why would we do that? Well, now the complete picture is almost here. If we have that this triangle is congruent to this triangle, As long as we state it properly, then all of the sides and all of the angles are congruent to one another. So we would have that A is congruent to C, which is what we want to conclude. So with BD congruent to BD, we have side, angle, side, side, angle, side. So our sixth step is to say that triangle ABD, make sure we state it correctly, ABD is congruent to triangle CBD. Oh, a couple of things here. I didn't justify step 5, and that's just the reflexive property of congruence. Everything is congruent to itself. And then step 6, right? This is just the side angle side postulate, where we're using the side angle side. So 1, 4, 5. And then the 7th step is, right, since these two triangles are congruent, we are able to conclude that angle A is congruent to angle C, because that's how we've written it. Right? Angle A is congruent to angle C. So again, when we say that triangle ABD is congruent to triangle CBD, we're saying that the angle at A is congruent to the angle at C in this statement. So we pluck that statement out of there. And this is simply the definition, by the definition of congruent triangles. And that's it. Right? We were able to conclude the angles opposite are congruent. Okay. So there is another proof for this same theorem. And it's worth looking at just because it's kind of interesting and it's a little bit shorter. And it's nice to see variations. It's nice to see different proofs. And it's short, right? If it were two really long ones, I wouldn't present them both. Even if they left me space to, I wouldn't. But this one is short, so we'll take a quick look at it. So we're trying to prove the forward direction of this, right? Assume that the two sides are congruent to one another. What we actually do is we first paste two copies of a triangle. So we have PQR and PQR, the same triangle, repeated twice. And we say that PQ is congruent to QR, but PQ is always congruent to QR. So we're emphasizing the fact that we have two triangles by, instead of saying that this side is congruent to that side, we're saying this side is congruent to this side. So it's a little bit different, but it allows for some shortcuts. So let's see here. So what we're given is triangle PQR with congruent sides PQ and RQ. Okay. Congruent sides can also be stated by that the two lengths of the line segments are the same. Equal, that's the definition of congruent line segments. So this is simply what's given. All right. Our next step is to look at angle PQR, which is congruent to angle RQP. Makes sense, they're the same triangle. It's referring to the same angle. So the third step is that we have triangle PQR is congruent to triangle, okay, PQR is congruent to RQP because we said this side is congruent to that side. PQ is equal to QR. So PQR is congruent to RQP. Oh, sorry, this was the reflexive property of congruent, right? Because it's the same angle, it is congruent to itself. And here, we want to be careful. While, yes, technically it's the reflexive property of congruence, we're also, right, to say the reflexive property of congruence, we would need triangle PQR is congruent to triangle PQR. But that's not what we have. So in order to utilize this, we want to recognize that the sides are this congruent. So side is congruent to side. And then the angles are congruent. Angle is congruent to angle. But then this also says that the side is congruent to the side. So this congruence here of the triangles is actually given by the side angle side, where we utilize this statement, and then this statement again. So we got to congruence of triangles in 3 steps instead of 6 steps. With the congruence of triangles, we can say as our last step that the angles of interest are congruent. Angle P is congruent to angle R. And that's just the definition of congruence, or of congruent triangles, rather. All right, we need all the sides and all the angles to be congruent. All right, so we're doing really well. We're doing really well so far. These remarks, I think I said pretty clearly while I was going through it, so that should be good. And let me just double check with where we're at here. So we've got about 3 pages left because exercises start there. So 1, 2, 3 pages left. So take a deep breath, right? This is really intense when we're giving lectures like this here. Just me blasting through material. It's pretty intense. So feel free to just take a moment, stand up. You need a drink? You're thirsty? All right. Oh man, you're prepared. Gosh. Okay. So are you good to go? You want to keep going? All right. Excellent. Well, let's keep going. All right. So the next thing we have is the equilateral triangle theorem. Now, this is the one that I had good notation for. Okay. Get rid of that N. A triangle is equilateral if and only if it is equiangular. So some of these words we're familiar with. Equilateral, we've heard that word before. Equiangular, right? I had to think about it briefly and say, oh, okay, I assume I know what that means, but I don't ever remember hearing the definition. But the same is true about equilateral. I always forget what triangle is what. What is an equilateral? But we can quickly deduce equa, right? Same. So lateral is actually referring to the sides of the triangle. Equiangular, that one's pretty obvious. Equa means the same. Angles. Okay, so what we're saying here is that all the sides of a triangle, so all sides are congruent if and only if all angles are congruent. So it's just a restatement of the theorem. I think it makes it a little bit more clear because we're not using fancy language, equilateral and equiangular. We're saying what those things mean. So good to go there. That looks good. Excellent. So the proof of the forward direction is an exercise in this section, whereas the proof going the other direction is not an exercise until the next section. I suspect that whatever technique is used to go the backwards direction is presented in the next section. Some other theorem or definition or something of that sort. All right. the exterior angle theorem. All right. The measure of an exterior angle of a triangle is greater than the measure of either, that erased off, is greater than the measure of either EI, there we go, of either of the non-adjacent interior angles. Okay, so that's a little bit of a mouthful. Let's take a look at a picture to see what we're trying to say here. I'd like to draw some straight lines. So I'm going to use this guy a moment. And we've got, all right. So we've got a triangle. Right here, this looks pretty good. Okay, so we have a triangle. This is an exterior angle. Okay, cool. This exterior angle and this angle are adjacent angles because they're next to each other. This angle is larger than this non-adjacent angle. And this angle is larger than this non-adjacent angle. And that's all that the theorem is saying. Okay, so we can prove this. And this is a two-column proof for us. So I want to label our vertices here, our points. Pencil, there we go. So we'll call this one A, this one B, A, B, and C. This point out here we'll call D. And we're going to end up picking up some other lines and angles as we move along, or lines and points, rather. Okay, so how do we handle this? Now, the first step is that we want to state that angle DAB is exterior to the triangle ABC. We drew it, we want to make sure we say it. That's just what's given. All right. The next step is, I didn't run through this quite clearly enough in the last couple of minutes to remember where we're going with this. So let me look at this a second. And be the midpoint of that. Okay. And we're going to show that those are, that's congruent. So that okay, well, we got this. Bear with me though as we move along. So let M be the midpoint of AB. Let M be the midpoint of AB. And this is given by the midpoint existence theorem. There's something different about this screen. I can't write small enough. All right. That looks somewhere around the midpoint. Okay. Next step. Well, since M is the midpoint, AM is equal to BM. AM is equal to BM. And this is by the definition of a midpoint. Okay, so let's take a line. Let's take a line from C through M all the way out to some point that we'll call P. But this point P is relatively specific. In particular, this point P is such that CM and MC, sorry, CM and P are congruent. Okay, so let's go with pencil again, and this is point P. So let P lie on CM, so it's the ray CM, such that M is between P and C, so C and C and P, so between this there, and the distance from M to C is equal to the distance from M to P. So we have that these two sides are congruent, or these two line segments, and we have that this line segment is congruent to that line segment. Excellent. Fifth step. All right. We have a pair of vertical angles here. So if we look at angle 1 and angle 2, those two angles are congruent because they're vertical angles of one another. Angle 1 is congruent to angle 2, and this is because they are vertical angles. So it's by the vertical angle theorem. It looks like I didn't justify this guy. How can we justify the fact that we can do that? Well, that's just by the ruler postulate. If you don't remember what all of these things are off the top of your head, that's fine. That's not a big deal. Just come back to this a little bit later and say, what are these things? And you can quickly find them in the preceding couple of sections. All right, step 6 here, what we've got next is we've got a pair of congruent triangles. All right, pair of congruent triangles. So we have, let's draw a line here again so we can clarify where these triangles are. So we've got triangle, we'll call it PMA is congruent to triangle CMB. So, triangle PMA is congruent to triangle CMB. And this is by side angle side, where we have M is the midpoint of AB, so AM is equal to BM, so that's line 3. And then we have the angles are congruent, so 5 for the angles. And then side, the other side, these two, 4, line 4 is where we created MC is equal to MP. So 3, 5, 4. If you wanted to list it 3, 4, 5, that's fine too. It doesn't really matter. This is just nice because it's side and side. All right. So what good does that do us? Okay. So the measure of angle DAB we can compare to, label them here, angle 3. I used red for angles earlier. 3. So this angle is congruent to this angle. And this angle is part of the larger triangle. Okay, I'll say that one more time. Angle 3 here is congruent to this angle. But angle DAB is clearly larger than angle 3 because P lies in the interior of angle DAB. So in this way, by constructing this very contrived congruent triangles, right, we've made this portion here, we've created this triangle, which has a point in the interior of angle DAB. Angle 3 is congruent to this angle, and P is in the interior of DAB. That allows us to make the comparison. So we say that the measure of angle, DAB is larger than the measure of angle 3. Okay, and what allows us to state that? That's the angle interior inequality. Angle interior inequality. Again, that has to do with if we have a point P in the interior of an angle, then the angle made by the ray or by the points P, A, B is going to be smaller than the angle that that point lies in the interior of. Excellent. Excellent, but we have again the congruence of 3 and B. Let's see here. Yep, okay. That's fine. I accidentally wrote some of these down in the wrong order. That's all. That's not a big deal. We haven't said anything wrong yet. Let's just state exactly what I said. Measure of angle 3 is equal to the measure of angle B. And this is by definition of congruent triangles. No problem there. And then number 9, we can use this substitution here to say that the measure of angle DAB is larger than the measure of angle B. Yes! Right, that was just a substitution. And we're so happy because that got us 1/2 of what the theorem is trying to say. And don't worry, we're not going to prove the other half, right? But let's quick finish this up. The measure of this angle is larger than that one by a substitution where we take line 8 and we plug it into line 7. Plug this one into there and it gets us this. So rather than saying that we want to do all of this work again, we simply say similarly, because as mathematicians we are a little bit lazy sometimes. Similarly, we have that the measure of angle DAB is larger than the measure of angle C. All we would have to do is construct, right, construct the same kind of triangle and do the same work to show for this guy. It's not same, but similar enough that we're not going to worry about it. Similarly, we have that. And that's exactly what we wanted to show. Okay, the measure of an exterior angle is larger than the others. That's it. Okay, so we've got about 20 minutes left yet in our lecture period, so we're not doing too bad because this is essentially the last page, because the last page is just part of the proof. So there's not much to write on this page. All right, so we defined perpendicular lines, I don't know what that word is. We defined perpendicular lines though, back in section 2. We'll look at the definition again because as we mentioned before, right, we have attempted to forget everything and now we want to reintroduce things. So let's take a look at perpendicular lines. So perpendicular lines can be defined in 2 ways. 2 lines that intersect to form a right angle are called perpendicular lines. Right? 2 lines that intersect to make a right angle are perpendicular lines. Or we can write it as 2 lines that intersect so that all angles formed at the point of intersection are all congruent, are called perpendicular lines. And yes, it is quite true, right? All of those will be right angles. Okay, so it's the same statement. In order for these 2 to be equal, these 2 to be equal, and those 2 to be equal, right, we would end up with 4 of the same measurement. Actually, let's not call it A, let's call it 4 lowercase a is equal to the total of the 360 degrees that are there, divide by 4, and you know, hey, look, they're all 90 degrees. Okay, so it's the same. So let's see here. Yes, the supplement postulate. If you take one definition, the supplement postulate gives the other definition, no matter which way you go there. To denote perpendicular lines, we can use this notation. And if you notice, right, we've talked about lines. We didn't say line segments. We didn't say rays, but it's the same thing, essentially. So it is worth noticing the definitions are for lines, right? 2 lines. But rays and line segments should also be considered, but the definition is the same. All right. A bisector, a line, ray, or line segment that intersects some other line AB at the midpoint of AB and nowhere else is a bisector of AB. There are many bisectors of a line segment. So, right, if I have a line segment AB, here is the midpoint M. I could have this line passing through. That's a bisector. But I could also take a look at this line, except for move it over a little bit. There we go. And that one is also a bisector. So there's, right, it doesn't say anything about the angle at which it passes through. If we do concern ourselves with the angle that it passes through, in particular, if it's perpendicular, then it's called the perpendicular bisector. And that is unique. There is only one. All right, so a point on the perpendicular bisector of a line, sorry, a point is on the perpendicular bisector of a line segment if and only if yes, if and only if, right? So point P, we'll say point P is right here, is on the perpendicular bisector if and only if the line segment from P to B and the line segment from P to A are congruent, right? If that's equidistant. So if and only if it is equidistant, from the endpoints of the line segment. Again, that distance is the same as that. All right. Like many other theorems, we're only proving one direction of the theorem. So the forward direction is left as an exercise. We'll take a look at the reverse direction. So we're going to assume that the distance from A to P and the distance from B to P are the same. And we're going to show that P must be on the perpendicular bisector. All right. So let's, I'm going to draw a picture of a triangle up here. And so we may have to scroll up a few different times to see it, but with how things have been going lately, I don't know that I can fit everything nicely onto the page if I draw it on the next page. So let's say we have a triangle. Where we have the points given as, we start off with the line segment from A to B. And we want to show that the point P, equidistant from A and B, is on the perpendicular bisector. So we have triangle APB. All right, so we're not given triangle APB. What we're given is P is equidistant from A and B. We need a 1 there. 1. There we go. And this is what's given. All right, so the next step is PA is equal to PB. Well, isn't that just what's given? Yes, that's what's given, but we're emphasizing here that that's the definition of equidistant. So what does it mean for P to be equidistant? Well, it means that the two line segments have the same length. All right. So here we have triangle APB, and we have that this side is congruent to that side. By the isosceles triangle theorem, we have that this angle and this angle must also be congruent. So angle A is congruent to angle B. And this is by the isosceles triangle theorem. All right, so we're going to pick out another midpoint. Let T be the midpoint of AB. All right, we're looking for P lying on the perpendicular bisector, so we need to recognize where that perpendicular bisector is. So the perpendicular bisector passes through T, and we know that this point exists by the midpoint existence theorem. So from there, a definition of a midpoint gives us that a T is equal to TB, since T is the midpoint of the line segment AB. Let's go ahead and place T on here a moment. Right, there's T. So AB is congruent to, sorry, AT is congruent to TB. Lengths are the same. And this is the definition of a midpoint. So like most other things, what we're going to try and do is we're going to try and create, I believe, a pair of triangles. And then we'll show that the two angle measures here have to be the same, and in particular, they have to be 90 degrees. Because once we have that, the line segment from P to T intersects AB at a 90-degree angle, then of course we have that is the perpendicular bisector. All right. So step 6 then is to create some congruent triangles So triangle APT is congruent to triangle BPT. APT is congruent to BPT. And that's because we have, as we mentioned just a moment ago, we start off with PA is congruent to PB. We noted by the isosceles triangle theorem that angle A must be congruent to angle B, and then T is the midpoint, so AT is congruent to TB. So by side angle side, we have that these two triangles are congruent. So I'm going to put in this line, and I'm going to make it red just for kicks and giggles. So that red line is what we're going to claim or show is the perpendicular bisector. And then obviously, since it's defined by P, P lies on it. So those two triangles are congruent. And from there, we have, right, congruent triangles immediately gives us that this angle measure is equal to this angle measure. So we'll call this angle 1 and this angle 2. And we have that angle 1 is congruent to angle 2. We said that these triangles were congruent by side angle side because of 2, 3, and 5, side, angle, side. And then these two angles are congruent because of congruent triangles. Definition of congruent triangles. All right, so once we have that, the next thing that we want to notice is that angle 1 and angle 2 form a linear pair. So rather than having to go through all the work, linear pair, they're supplementary, their sum is 180 degrees. That supplement postulate that we talked about last time, we can just immediately say that their sum is 180 degrees. So the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees by the supplement postulate. But we have that the two angles are equal to one another. And actually, it looks like here, I really wanted to say that the measure of angle 1 is equal to the measure of angle 2, rather than just the two angles are congruent, which is still, that's the same thing. But this a little bit more explicitly allows us to perform a substitution. So we could say that measure of angle 1 plus the measure of angle 2, a substitution, measure of angle 1 plus the measure of angle 1, use this substitution to replace 2 with 1, is equal to 180 degrees. And this, again, is a substitution of line 7 into line 8. And then we can use some algebra to give us that the measure of angle 1 is equal to 90 degrees. Algebra. And then our last and final step, right? This immediately gives us that this line is the perpendicular bisector because the two lines intersect, forming a 90-degree angle. So that gives us PT is the perpendicular bisector of a B. And that is simply the definition of perpendicular bisector. In particular, we're looking at lines 5 it's the bisector and line 10, which shows that it's perpendicular. So 5 and 10. And that's it. All right, yay, perpendicular bisector. And again, the end of the section. So I'm gonna call that good. I'll scroll back up so you can see that in case you have anything to copy yet. And I'll just say that I'm really happy that we were able to get through before class was over. It means that my videos, hopefully for the most part, are staying consistent with that. I don't want to exceed, right? I don't want my videos each week to exceed the amount of time that we would spend in class normally, right? Because I'm trying to make an even trade of content for work. So, so hopefully you feel that way. And as long as I can, I will produce the videos. I'm going to stop the share a second and unplug this. As long as I can each week, I will continue to provide the content videos for us to be able to work on homework during lecture, unless the majority of you feel that I should do differently. The exception obviously is this week, and then it's possible that next week I might have some issues as well, because this week all that I've been doing is grading because we had a bunch of exams last week. So I may have troubles next week. I don't know if this is going to turn into a snowball effect or not. I'm hoping not, hoping that we can continue with the content videos. So as long as it's possible, I'll continue to do that, but certainly we'll leave it open for discussion next week. So awesome. Any questions? All right, cool. So we'll call it good and have a wonderful day.
Good.